Swayam Prabha. Digital India. Educated India.
In the last lecture, we looked into the mathematical formulation of a beam with piezoelectric patches for energy harvesting applications, and we followed a paper for that. Today, we will look into the same formulation, but from a different perspective. We will start with the governing differential equations and we will do the formulation. So, in the previous lecture, we did it by starting from the Hamilton's principle, and there we put the approximations. Here we will start with from the governing differential equation and we will do it, and after that we look into the vibration control applications. So, the governing equations in general for a 3D case, as we have seen, that is this sigma I j comma I plus B j, which is a body force, is equal to rho u j double dot, and the other differential equation for the electrical domain is the Gauss law. Now, for if we again have our beam under consideration, and if we have x as the axial dimension, z as the vertical dimension, and y is the other out of plane dimension. So, let us consider this, and with Euler-Bernoulli assumption and piezoelectric effect under Euler-Bernoulli assumption and considering piezoelectric effect, the linear momentum equation becomes this. The corresponding governing differential equation is mb w double dot plus del 2 w by del x 2 of E I total del 2 by del x 2 of E I total del 2 w by del x 2 minus P z minus del 2 m p by del x 2. So, we are very familiar with this equation, we already derived it, and for the other equation is just this, the Gauss law is just this, considering the fact that these piezoelectric patches are polarized in z direction, and so all the electric field voltage are in the z direction, electrical displacement in z direction. So, these are the two equations now that we have to use to form the final energy harvesting equation, and here we will follow the notations that we were using in the strain induced actuation problems. So, in the previous lecture we used the notations that was in the paper, but here we have come back to the notations that we are using in the induced strain actuation problems. So, let us assume W as we have assumed phi Wj, Q Wj, and the electric field was assumed to be, let us assume the electric field. So, Ez equal to V, the voltage which is a function of time, multiplied by psi, psi is a function of z, and here Q W j is also function of time. So, we will make these assumptions and then we will go to the derivation. So, our approach is to multiply the first equation by phi W j. So, if we do it, so let us multiply it by phi W I, let us take I as the index, and then it is we are just multiplying phi Wi with the first equation, and in the first equation we put these approximations and we integrate it from 0 to L, and MP is, as we know, as per the definition, MP is the area integral of minus Z into elastic modulus multiplied by the free strain, and free strain, as we know, that it is D31 multiplied by electric field Ez or E3, whatever, Ez is equal to E3, and we have already assumed Ez as this. So, finally, after putting these approximations and following the procedure that we have followed, finally this gives equation in this form. So, we have already seen how to derive the set of ordinary differential equations from this kind of equations. It needs some shifting of derivatives also, which we have to do, and finally, if we do all these things, these equations comes. Is equal to F say. So, here F M I j is, you can put Q W, M I j is M B phi W I phi W j dx, which is equal to M S I j plus M P I j as per the paper discussed. So, as per the paper discussed, and then we have K I j is equal to E I total and which is equal to KSij plus KPij as per the paper. So, we are just showing the equivalence between the expressions using the two different formulations and notations, and we have phi I which is minus 0 to L A Z psi D31 Young's modulus multiplied by phi I comma xx dA dx. Now, please understand D31 multiplied by E gives us E31, and so this is phi. So, we are using phi here itself, and Fi is 0 to L phi Wi Pz dx. Now, here by assuming Pz to be a distributed function of x, it is written in this way. While discussing the paper, we saw that those forces were considered to be discrete. So, that is why they were summed over. So, that is about the first equation. In the second equation, which is dz is equal to 0, we multiply psi and then have V and then from there we can show that this becomes q multiplied by, so q, let us put capital Q as charge. So, capital Q is equal to charge because we are using small q to denote the coefficient associated with the displacement components. So, it is ds plus V dz psi multiplied by V, and then dV. So, now this term can be written as, we can sum it over. So, we can write phi Wj comma xx q Wj plus E3, so electric field, so which is psi multiplied by V and that multiplied by epsilon 33. So, here to multiply E here E31 and this is epsilon this multiplied by psi dV plus q multiplied by psi ds. So, this gives us the equation as psi phi t multiplied by q w plus Cp is just one value here. So, we may just write it as Cp Cpv plus q is equal to 0. Phi t we have already defined. Cp comes to be volume integral of epsilon 33 epsilon sigma square dV. So, we have got these two equations. The first equation, from the first equation, which was a version of the linear momentum equation. We got this from the first equation, which was a version of the linear momentum equation, we got this equation, and from the second equation, which is Gauss law, we got this equation, and these two equations are equivalent to the equations that we got in the last lecture while discussing the paper in a different type of formulation. Now, we look into vibration control applications and the corresponding mathematical analysis. For that, this paper by Gaudenzi and his co-authors can be referred to. Here the idea is that we have a piezoelectric beam, a beam which has piezoelectric patches for sensing and actuation. So, it has two piezoelectric patches at the top and bottom. The first top one is used as actuator and the bottom one is used as sensor. Now, it is not needed that the actuator and sensor has to be placed back to back, they can be placed at other locations also depending on the control strategy. Now, from the piezoelectric sensor, so this structure is under some dynamic load. So, that in the experiments the dynamic load can be given by a shaker or anything. In real life it is due to the external factors. So, it is under some dynamic load, and then so we can just show some loads here. We can denote this as Pz. Now, from the sensor the charge output comes, and then there are two modes as suggested by this paper. One is the charge amplifier mode, through which we get voltage from the charge. So, voltage output from the charge. So, it can be a charge amplifier, or there can be current to voltage converter. So, we will talk about it, what it is. Then from this the voltage output comes, and then it is multiplied by a gain. So, we can call it controller, and then finally, from there a feedback voltage is given here, which we may call V voltage. Now, from here the charge or current comes here, the output of this charge amplifier or current to voltage converter is a voltage. This voltage, when it goes to the controller, it is multiplied by a gain, and then the final voltage comes here, which actuates the actuator. Now, if you are interested in the details of this charge amplifier or current to voltage converter, this paper can be referred, the circuit diagrams are given there. Now, if we write the dynamics of this, then from there the charge can be written as charge output from sensor is Q, which is equal to dz integrated over the area. So, we have the electrical displacement dz here, let us call this as x, this dimension as z, and this let us call this as y. So, the same convention that we have been using. So, the dz here and it is already normal to it is already oriented along the z axis, which means it is already normal to the xy plane. So, dz integrated over the area, that gives us the charge output q. Now, the charge output q is E31 of the piezoelectric material multiplied by the strain. So, the strain there the strain here is nothing but epsilon 0 minus z into kappa, as we know. Now, epsilon 0, so strain is equal to epsilon 0 minus z into kappa. So, epsilon 0 comes here, z for this case is this, and we have to multiply kappa here, and kappa comes here. Now, the thickness of the piezoelectric thickness of the host beam is Tb, and we can call the thickness of the piezoelectric patch which is used as actuator to be Ta, and the thickness of the piezoelectric patch which is used as sensor to be Tcs. S stands for sensor, Ax stands for actuator. Now, with this we can rewrite this expression as integral from x 0 to x 0 plus L c, and again if we want we can call this as x 0 as we have been calling, and this dimension, it is better to show in a different color just to avoid confusion. This dimension is x 0 plus L c. So, we are assuming that the length of the sensor and actuator same. Again, that is not a requirement, they can be different as well. So, we are assuming L c, that L c s is equal to L c a is equal to L c, but that is not a requirement, they can be different as well. Now, we also know that in our analysis we have been assumed u 0 x t to be summation of j is equal to 1 to m multiplied by q u j into phi u j into q u j, and w as n phi u j q w j. So, with that approximation this expression can be written as E31 multiplied by Bs. Bs is the width of the sensor, and then we multiply this row vector q u 1 x to q u m x, and then we have Tb plus Tcs qw1 x double dot w comma xx plus Tb by 2 plus Tcs and this entire row vector is multiplied by the column vector, then dx. So, what we are doing is, if I multiply this q vector with this row vector, that gives me this expression. Now, we can write this entire expression as AT multiplied by q. Q is this column vector and AT is this vector multiplied by Bs into E31 and integrated from x0 to x0 plus Lc. So, here AT is of size 1 multiplied by m plus n, and q is of size m plus n by 1. So, again just to summarize, what we have done here is we need the expression for charge from the sensor. So, charge is integral, surface integral of the dz, and dz is E31 multiplied by the strain. So, E31, and the strain expression is here in terms of epsilon 0 and kappa, and epsilon 0 and kappa comes in terms of the derivatives of this phi u and phi w. Okay, here this is not q, this is phi. And when this vector, after being multiplied with Bs and E31 integrated along the length of the sensor, it gives me a vector called A. Now, we have to write the expression for the voltage that we get from the charge amplifier. If you want the voltage from the charge amplifier, the voltage that we get is VA is equal to 1 by Cf multiplied by Q, where Cf is capacitance of the or we can call feedback capacitance of the charge amplifier, and then this expression can be written as 1 by Cf multiplied by the A vector multiplied by the Q vector. So, the input voltage to actuator can be written as V is equal to, we multiply by some gain G A with the V A. So, it is G A by C F A T Q, and current to voltage converter for that the voltage, let us write it as maybe V C is R C V multiplied by Q. So, R is a resistance. If we look at the structure diagram of the current to voltage converter, the position of R is there. So, R multiplied by Q dot, Q dot is the current. So, that being multiplied with the resistance gives us the output voltage from the current to voltage converter, and so that is equal to 1 by Cf multiplied by AT into Q dot, and again input voltage to actuator is V is equal to let me call it there is another gain. So, let us call it maybe G V multiplied by V C. So, we can call it G C also. So, it becomes G C, right, it is not R C. RCV. So, G C multiplied by RCV AT Q dot. So, what happens is the charge amplifier gives a output which is our VA or VC, and accordingly the controller multiplies with GA or GC, and the product of it is the feedback voltage V that comes to the actuator. Now, we know that for the actuation case, we have already seen that the dynamics can be written as this, and that is equal to x 0 plus L C B T N P M P, and here we can B T is already known to us, and this is multiplied by N P. So, it gives, and then it is integrated over the domain of the piezoelectric actuator, I mean the domain along the x axis, and that gives me the actuation force. And then we can write this entire thing as B I. So, we are calling it B I, means this B matrix integrated over x 0 to x 0 plus L C. So, B I multiplied by a vector S, we are introducing a new vector S into the actuation voltage V. So, S is a vector which is required to convert the voltage V to NP and MP. So, NP and MP is a vector S which on being multiplied with V gives me the NP and MP. So, S can be written as a function of, in terms of TCS, the width of the TCA actuator, the width of the actuator BA, and the beam thickness TB, and the elastic modulus of the piezoelectric patch, and D31, or we can write E31 also. So, in terms of those, this can be written, the S vector can be found. So, we have now this, and then we can rewrite the expression as M Q dot plus C multiplied by Q plus K Q. And then we have the B I, we have S, and then we have G, the gains G A divided by C F multiplied by A transpose multiplied by Q. Now, this is for, okay, we will do that. Now, again this we can, this entire expression can be written as L A multiplied by Q, because we know that this is M plus N over Q, S is 2 by 1, this is 1 by M plus N, and this is 1 M plus N by 1. So, finally, this comes to be M plus N over M plus N, and this we know it is M plus N over 1. Now, this is charge amplifier mode. Now, when for current to voltage mode, the same expression for current to voltage mode, it becomes this becomes LC over Q dot, and where LC is BI over S, then we have GC RCV, we defined GC RCV, and we have A transpose. So, for the charge amplifier mode we have Q here, and for current to voltage mode we have Q dot here. So, we can see depending on the control strategy, whether we use charge amplifier mode or current to voltage mode, we have Q or Q dot here, and the gains are decided depending on, it is a matter of control system. So, we used various techniques, various optimizations to find out the optimal gain, so that this entire system can be controlled. Now, in real life there can be unwanted vibration due to several reasons. Aeroelastic instability for aircrafts can be one of the reasons. So, when it goes to the unstable region, dynamically unstable region, flutter can occur and the vibration may look like this. In such cases, if this kind of controls are applied, then the vibration can be stabilized. So, we have discussed about the energy harvesting and the control systems based on the formulations that we have been doing so far. Now, with that, let me conclude this lecture. Thank you.